Hi, Year 12s. We're going to talk about polymers in a bit more detail. So we have talked about proteins, which are a form of polymers made up of monomers, and we specifically talked about proteins which have amide or peptide links. But there are more polymers that can be formed than those that are just made up of amide or peptide links. So, for example, if you've got ethene here as your monomer, which has a C double bond C component to it, and you do a reaction where you actually add them to each other, add all these monomers to each other, and you just imagine that double bond folding out to another ethene molecule which has that double bond fold out. You can actually get polyethene, which you may have actually heard of, which consists of all these monomers joined together. And so you get the repeating unit down here. And this is how, if we ask to draw a repeating unit, you draw it around the monomer. If it's got bonds, which it will through it, you just draw the square brackets through the bonds, and then you put a little n on the outside of the bracket. So naming these are really simple. You just add poly to the front of whatever it is, and it will become a small letter. There are two main types, and we've talked about condensation polymers because that's how you form a protein. But you can also get addition polymerization. And the main way you can distinguish between the two is if you've got an addition polymer, the monomers will contain a double bond so that you can unfold them in order to form this backbone. Or if you're alternatively looking at the polymer and wanting to see if it's formed from an addition reaction or a condensation reaction, you just look for a carbon chain backbone that just has single carbon bonds to it. Condensation polymers can be formed from NH2 and COOH, as we've talked about with proteins, but they can also be formed from OH and COOH. If you lose the OH from the COOH and lose the H from the OH and combine them, they'll form water, and then you can combine the different monomers. So they can either have an ester functional group or an amide functional group in between the monomers or the repeating units. So if we think about a bit more about addition polymerization, the way they are formed is you break them. You break those double bonds to form this carbon-carbon single bonded backbone. But to do that, you need an initiator, so that's just something to start the reaction. You need heat and you need pressure. Condensation polymers, they'll contain those two different functional groups that can undergo condensation reactions. You'll produce water, or water will be lost, and so then you get polyesters or polyamides, which we've talked about before. So polyesters, if we're just going into a little bit more detail, you have to be able to draw the structural formula of a polyester given the structural formula of the monomer, or vice versa. So if you're given a monomer, you should be able to draw the polyester that forms from it. Alternatively, if you're given a polyester, you should be able to draw the monomer that forms from it. So polyesters will look like this. You have to have a diol and a dicarboxylic acid. So that means that you have a carboxylic acid, but it's dicarboxylic acid, so it's got carboxylic acid functional groups on the end, and a dialcohol where it's got alcohol groups at each end. And you combine those both together to get the polyester. That will lose the OH, that will lose the H, they'll combine together and you'll form the polyester. Hopefully you can see if that OH goes away, that H goes away, and you connect the two. So you connect that carbon to that oxygen. You get this down here. This is the repeating unit. Alternatively, you can just get two of the same monomer. So if you've got, instead of having a dicarboxylic acid and a dialcohol, so a molecule that has the same functional group but has two of them, you can actually get monomers that have both a carboxylic acid functional group and an alcohol group. So they're called hydroxycarboxylic acids because they've got a hydroxy group, an OH group, and a carboxylic acid functional group. If you combine both of those together, then you will also get a polyester. You lose the the H from here, the OH from there, they combine together. So we've just got some examples of polyesters here. This is polylactic acid. And as you can see, this has got a carboxylic acid group and an OH group. So this is a hydroxycarboxylic acid, whereas this here, polybutylene succinate, is formed from succinic acid and one for butanediol. So that's formed by a diol and a dicarboxylic acid. So similarly, you can have amides, polyamides, and they're either going to be formed by a diamine or a dicarboxylic acid. They'll always contain the amide functional group, but if you've got a dicarboxylic acid, then you'll form a polyamide of this form. And you just have to be careful. I guess the big thing to be careful about is how you draw them out. So make sure you draw them really accurately from the monomers. But you can either form them from a dicarboxylic acid and a diamine, or you can form them from an amino carboxylic acid, which contains an amino functional group and a carboxylic acid functional group on the same monomers. Either way, they both form polyamides, losing the OH from the carboxylic acid portion and the H from the amino portion. And so some examples here, here's your amino carboxylic acid or your amino acid, right? Every amino carboxylic acid is actually an amino acid if it's connected to an alpha carbon. An alpha carbon being that carbon that has an H on it and an R group and an NH2 and a COOH group on it. So if you combine amino acids together, you get polymers, as we've talked about with proteins. But you can also do it, as we've talked about, with a dicarboxylic acid here, where you've got the two carboxylic acid functional groups, and the diamine, where you've got the two amine groups, and they join together. Here your repeating unit is quite long, because you have to make sure with your repeating unit that it contains everything that exactly repeats. Okay, so when we produce polymers, we can produce them actually synthetically, which means we can actually make them in a way that we want them. So we can make them in a way that's actually conducive for whatever specific use that we want, and therefore to have the properties that we actually want. And so we can use it for plastics, fibers, paints, lubricants, adhesives, all different types, because we can control a few things. We control the chain length, we can control the amount of branching, the amount of cross-linking of the polymers, so that's linking between different chains, the polarity of side chains, and if we add in any additives. They do, however, have some disadvantages, and you do need to, for the sake of this course, know some advantages and disadvantages. So they're susceptible to UV degradation, which means they can be broken down by UV light. They're also heat sensitive, especially thermoplastics. Hopefully you remember thermoplastics, thermoset and thermoplastic polymers, two different types. But they're also non-biodegradable, so they're not easy to break down. Whereas the advantages are that polymers can be cheaper and less dense than glass. They can also be non-corrosive or non-corrodable, that's probably not a word, but they don't corrode, and so you can use them instead of metal car parts, and they can be cheaper and less dense, so way less. And they're often cheaper and more durable than wool and cotton for textiles. So just remember that you do need to be able to describe the advantages and disadvantages. All right. So we've also got to talk about and be able to compare the physical properties of polymers with different degrees of cross-linking and secondary interactions between polymer chains. And hopefully that will make sense. You'll be able to think about the physical properties like melting point and boiling point by comparing the different degrees of bonding between chains. And we will also want to be able to compare the effects of heating on thermoplastic and thermoset polymers, which we have talked about a little bit about before. So when we've got different polymer chains, like different protein chains, we can actually bond them together. They can by secondary interactions, or sometimes even by stronger interactions by that. But that is determined by the polarity of the side groups. So go back to amino acid, way at the top. And each of these amino acids, where is my amino acid? Oh, I'm thinking about the wrong booklet. So if you remember back to amino acids, let's go back to amino acids so you can see it. But remember, you have these R groups, these side chain groups there. So our physical properties are determined by those side chains, and they're also determined by the main chain links. So what the actual carbon chain is framed from? Is it from the carbon-carbon backbone, or is it from an amide or peptide backbone, or is it polyester? What is it? So if you've got non-polar side groups and non-polar main chain links, so you've just got carbon-carbon backbone, you're going to have dispersion forces. And therefore, as the length of the polymer chain increases, the strength increases because you've got a larger molar mass and therefore more electrons, more likely to have that temporary dipole form. If you only have dispersion forces, you're going to be flexible, soft, non-elastic, so you can stretch it, you can bend it. You'll have low melting and softening points, and you'll be able to be reshaped with heat. Because if you remember, dispersion forces are not very strong. They are present in all polymers, but they're weak compared to hydrogen bonding and covalent bonding. If you, however, have these NH groups, C double bond O groups, then you can actually get hydrogen bonding between the groups in side chains, or if it's in the main chain. So remember those, if it's a polyester or polyamide, those groups may very well be in the main chain, but they could also just be in the side chain. They are stronger than dispersion forces, and therefore if you do have hydrogen bonding and the potential for that, the polymers will be stronger, more rigid, and more elastic. Okay, so you'll be able to stretch it, but it will actually come back because the bonding will bring it back. Whereas if you've got dispersion forces only, if you stretch it, it's liable to stay stretched because there's not really strong forces pulling it back together. If you do have covalent bonding, like these sulfur-sulfur bonds we talked about in proteins, like the disulfide bonds, they're called cross-links. And if you increase the number of cross-links, it's going to get more rigid because they're stronger. It's going to get more elastic. It's going to bounce back quicker, and it's going to be harder. And you can actually add that in through something called a cross-linking agent, which you don't really need to know much about, but it's good to know that it exists. So if you remember us talking a bit about thermoplastic and thermoset polymers, thermoplastic only contain dispersion forces or hydrogen bonding, so only really secondary forces. And so they will soften when heated, and they will harden and become more rigid when cooled. They can be recycled by heating and reshaping. So you can actually recycle them because you can heat them, they become flexible, you can reshape them into different things. They're not that elastic, they won't bounce back. If you do cool them, however, the bonds will get stronger again. Thermosets do contain a high degree of cross-linking. They don't soften or change shape, so they will actually char or burn because what's happening is not those covalent bonds, they're not stretching, they're actually going to break. And so then the polymer itself will decompose and they cannot be recycled. So you can get polymers from fossil fuels or you can get them from renewable resources. And about 6 to 8% of the total global production of petrol is used to produce actually synthetic polymers, which you may not have realized. You do need to be able to talk about the advantages and disadvantages here. So the advantages of making polymers from fossil fuels is that fossil fuels are still relatively abundant. There's a lot of them. We still use it a lot. Petroleum is actually really easily extracted and processed, and there's a lot of existing infrastructure and industries for producing it. There are a wide variety of polymers that you can actually produce from petroleum. But as we know, it is non-renewable, and therefore it will contribute potentially to the greenhouse effect. And we're actually using up our reserves of fossil fuels much faster than they're getting replenished. And you do know all of that, but that's just a reminder of the environmental chemistry topics that we've done already. So they are the disadvantages of using petroleum to make polymers. So because of that, we're actually trying to produce biopolymers, where we can make polymers from not renewable resources, not non-renewable resources. And so they're derived from biomass. And so some plants, starch and cellulose can be used for that. Proteins and oils can be also used from that. So plants can be used to produce these polymers. Now, of course, there's obvious advantages that they're a renewable resource, so that counteracts what we were talking about before, and plants and crops are relatively abundant. They're relatively easy extracted and processed, and we've already got systems for doing that. And byproducts can be used as a source of a biomass, so you can actually reuse some of those in order to be able to derive polymers from them. But the disadvantages of that, one of the biggest ones is a competition with land for food production. So if you're in a developing country, maybe a company will come in and will offer you a lot of money to be able to produce bioethanol, but maybe that means your country is actually not getting much food made. So there's a really, but if you're a farmer, you're going to go with not the altruistic thought, probably. You're going to go with what's going to feed your family. And so you might choose to grow bioethanol that gets shipped overseas or something like that. So that's one of the really big issues. It is still a relatively new area of research. And so therefore there's not a massive amount of polymers that are being made from plants. Okay, so the final thing we just want to talk about is why some polymers are biodegradable whilst others are not. So many synthetic polymers are not biodegradable due to those covalent bonds that if you break them, they're actually going to break. And so once they're broken, you can't really put them back together. At the moment, we break them down naturally in the environment, however. So all natural polymers can be broken down naturally in the environment, because if they contain ester or amide functional groups, you can undergo hydrolysis. So hopefully this is bringing back what hydrolysis is, when you use water to break up an ester or an amide. And so that will cause the polymer to break down into two smaller molecules, such as, now this is a new word, oligomers, which is just a few monomer units, dimers, which is two monomer units, or monomers. So an example of a hydrolysis of it, if you use water, you can break this molecule up here into the alcohol and the carboxylic acid. You can also get polymers that break down if they're exposed to UV light. They often include polymers with a large number of carbonyl groups, or polymers that have light-sensitive molecules added to them, which do exist. So we want to explain the advantages of polymers being biodegradable. That's pretty obvious. It's going to reduce the amount of waste in landfill, and when decomposed, it can be used as a fertilizer for growing crops. But a disadvantage, of course, there's a limited number of synthetic polymers that are biodegradable. So it's more the natural polymers, not really the synthetic polymers. And oxygen and water are required for decomposition. So you may have heard about like how there's been problems with recycling and things like that recently, that our recycling that we send overseas isn't actually really being recycled. It's just standing in piles. And so if you've got biodegradable polymers that are still in piles and covered up by a whole lot of other different waste products, they're not going to be exposed to oxygen, unlikely to be exposed to water, and therefore unlikely to actually biodegrade. When they biodegrade, they also release greenhouse gases. Okay, so there's some disadvantages. There's polymers for you.